All right, so when it comes to second derivatives, basically means that if you're given an equation, you derive it twice. So if I have y equals x squared and I derive it the first time, it becomes 2x. Derive it the second time, it becomes 2. When we derive it the second time, we'll notice certain things. So for example, this is a smiley face parabola, and this is a straight line, and this over here is a positive value. Let's suppose I got y equals negative x squared, which is a sad face parabola. When I derive this function, it becomes negative 2x. When I derive it again, it becomes negative 2. This is a negative value. This is a negative gradient as well. So what do we have here? We have a test for whether we are dealing with a minimum or we're dealing with a maximum. And the moment that the second derivative becomes greater than 0, then we're dealing with a minimum. And if the second derivative is less than 0, we are dealing with a maximum. So we got minimum and maximum, and we can also see that minimum also implies concave up. This is concave down. So second derivatives can give us the concavity, and it can also decide what are the extrema or extreme points. Are they maximums or minimums? And by rule, second derivative greater than 0, minimum, which is like the opposite. Greater implies minimum. Second derivative less than 0 implies that a maximum exists at that point. At some point, a curve may lie in a juncture where it goes through something like this, in which case there is no maximum and no minimum. There's a distinct maximum over here, there's a distinct minimum over here, but at a point where there is no maximum and no minimum, we're saying that the second derivative would be equal to 0 at that point. And the only time a second derivative would be equal to 0 would be in an instance where we're saying that the gradient is about to reach a maximum, but then it turns the other way. This is in a cubic function scenario. All right. Now, the second derivative is also equal to 0 at some x value as well. So that can also be substituted in as well. The second derivative being equal to 0, we're saying, is where we have what is known as a point of inflection, where it's concave up and concave down. So it's almost like bringing these two graphs together, but then removing that part. So the minimum and maximum sort of doesn't happen, almost happens, and then goes the other way. All right. Let's look at a scenario where we have a point of inflection. Okay, so let's suppose I've got the function f of x equals to x cubed minus 3x squared minus 144x plus 432. If I derive it, I get 3x squared minus 6x minus 144. If I derive it again, I get 6x minus 6. So if I make this equal to 0, which is the second derivative, I will get x equal to 1. So that means this curve, which is, by the way, going like that, because the a value is positive. Remember, when the a value is positive, the graph does that. When the a value is negative, the graph does that. It goes down first, up, and then down again. So from this here, at x equals to 1, we're saying there is a point of inflection, which means that the graph is going to probably have some kind of curve. And at that point there, somewhere, we don't know where it is, right? There's going to be a point of inflection. Let's just say it looks like that. And I'm just going to sketch it quickly. So this is curve. If I trace down, I can see this is the value 1. And that's my point of inflection. I can then substitute the 1 back into the equation, and I can get the coordinate of inflection. So I could change this into 1, change it into 1, change it into 1, put it on a calculator, and it will come to 1 cubed plus 3x squared plus minus 144 comes to 432. No, 286. 132 comes to 286. So this y value, corresponding y value, will be 286 compressed in this diagram. And that's an example of a point of inflection dealing with a cubic function. When it comes to parabolas, there's no point of inflection. And just as well, I mean, if you have a parabola which is y equals x squared plus 2x minus 1, and you find the first derivative, you end up with 2x plus 2, and you find the second derivative, you always end up with a number. So which means when you derive a cubic function, you end up with a function. Which means that this here is saying that it is greater than 0, so it's a minimum. And we know it's a minimum because that a value is positive. It's a smiley face. When it comes to the previous function and we want to find the turning points and decide whether the turning points are minimum and maxima, so that's over here and over here. If I have those coordinates, and I have that specific x value and that specific x value, I could then test it in this equation. I could say, okay, well, let's put a value over here that's a minimum and a maximum. How do I get this x value? How do I even get this x value? This is where the gradient is 0. So I would take the first derivative, make it equal to 0. And I would take the second derivative, make it equal to 0. And then find x. Your x value here ends up at negative 8. And this x value ends up at 8. And then I substitute that back into the original function. That comes to a y value of 972, and this comes to a y value of negative 400. And so I can get the turning points. So if I substitute each of those values now into my second derivative function, I can test it. So if I test it over here, my second derivative at 8 is going to be 6 times 8 minus 6. That's 48 minus 6, which is 42. So this is greater than 0, implying that this is a maximum. So suppose you don't have this graph, but you have that, and you found your coordinate. You could then realize the graph is going to reach its peak at that point, its maximum. And when you substitute, sorry, it's negative 8, and it's going to be less than 0, implying a maximum. And when you substitute positive 8, all right, negative 8 is supposed to be negative 48 minus 6. Negative 48 minus 6 is negative 56. Negative 54. That's going to be less than 0. Substitute 8 in there, remember we got 42 is greater than 0. That's going to be where the minimum lies, which is over here. All right, so we end up with this cubic function, which looks like this. And when I look at this cubic function, what I notice is that at this point, the derivative is equal to 0. At this point, the derivative is also equal to 0. At the first point, the second derivative, the maximum, is less than 0. The second derivative is greater than 0. And at the point of inflection, the second derivative, so double derived, is equal to 0 at that point. And going through some x and y, these are my roots of my equation, which is my x values of my original equation. And that's when the original equation is equal to 0. When you make your y value equal to 0, you find your x-intercepts. So just looking at all the different parts, breaking down when f of x is equal to 0, when f dash x is equal to 0, and when the second derivative is equal to 0, greater than 0, or less than 0, we have that. This is your point of inflection. That is maximum. That is your minimum. And the point at which the derivative is equal to 0 is known as stationary points. Stationary points.